All right, I'll cover that again briefly. If you're presenting, make sure you have the chat tab open so you can see my 5-minute warning. Keep yourself muted unless you're speaking, just for common courtesy. And nobody said that they don't want to be recorded. If you change your mind on that, let me know. So far, the recording is just going to be playing the entire time. We're going to start in a second. We're aiming to finish around 1:20 or around 1 to start a 20-minute discussion. We're going to start in a second with Marie Ramel-Delobel, Thomas Godon, Lény Grassot, Delphine Praud, Beatrice Rivers, and Pietro Salizzoni. Please take it away when you're ready.
Yes, so I'm going to share my screen. So, do you see my presentation on your screen?
Yeah.
Okay, so perfect. So, hi everyone. My name is Marie Ramel-Delobel. I'm a PhD student and I almost start my second year at the Centre Léon, which is a research center against cancer located in Lyon, in France. And I am also at the laboratory of fluid mechanics and acoustics at the École Centrale Engineering School of Lyon. So my work aims to develop a method to estimate the pollution exposure by taking into account daily mobility. This method is made to be applied into epidemiological studies about chronic diseases and most particularly about risk of breast cancer. So breast cancer is the most common cancer in women worldwide. The increase of the incidence of this type of cancer in the past years is associated with widespread screening, menopausal hormone treatments, or lifestyle changes. However, the role of environmental factors is also suspected, and several epidemiological studies suggest a link between long-term exposure to ambient air pollution and breast cancer risk. Nevertheless, there are still uncertainties, mostly because the causality of chronic diseases and cancer is due to many factors which interact together. Also, because the time between the first exposure and the occurrence of the disease can be very long, it makes difficult the identification of the relations between a factor and a disease. Consequently, it is aimed to quantify exposure over a lifetime, but this is quite a challenge due to the lack of data. This is therefore the context of my thesis and the APOPCO research project set up by the Cancer Prevention and Environment Department of the Centre Léon in Lyon. So the particularity of the APOPCO project is to develop new methods applicable in epidemiological studies in order to provide more accurate exposure data. So due to a general lack of information on subjects' activity and mobility patterns, epidemiological studies on air pollution usually estimate exposure based on their residential address of the subject. So this can lead to inaccurate estimates, and the aim of APOPCO project is therefore to take into account exposure both at home, at work, and during commuting. So to estimate the association between exposure to air pollution and the risk of breast cancer, the data used are in a case control study nested in the French national E3N cohort. So the study is based on nationally available data for 10,000 women over a 22-year period. And the three pollutants are mainly considered, so namely NO2, PM10, and PM2.5, as they are suspected to have an impact on breast cancer risk. So the method implemented is developed along 3 dimensions. So firstly, the spatial dimension by testing the method on the scale of Lyon metropolis so that it can be extended to the national scale with a view to its application in the APOPCO project. Secondly, the temporal dimension, so in order to be applicable over the 22-year study period, or even on lifetime scale if the data are available. And finally, it must be easily transposable to other studies based on the information of the origin, the destination, and the mode of travel. So the method is semi-automated through an R programming script. So the method is divided into 6 main steps. So the first step consists of estimating the ambient concentration on the road network. So to do this, pollution concentration are extracted from the land use regression model and associated with the transport network. So then the concentration obtained are weighted by the time it takes to travel along each section, depending on the speed of the mode that people are using. So car speeds are assigned according to the average speeds estimated in the BD Topo, which is a database from the French National Institute of Geographic and Forestry Information. And the speeds attributed to active modes are extracted from the N-Worth Physical Activity Compendium, which attributes an average speeds to go to work of 16 kilometers per hour for cycling and 5 kilometers per hour for walking. Then, taking into account commuting in the estimation of exposure involves recreating the routes that individuals are likely to take. So a number of routes are thus calculated for each subject according to the mode of travel they use. For each mode, a specific network is created by removing roads where the mode cannot travel, so such as motorways for cycling and walking, or cycle paths, pedestrian areas, or stairway for cars. And in the second step, a set of 5 routes is calculating by weighting the calculation according to certain criteria. Among these 5 routes, we have the shortest routes in terms of length, the shortest route in terms of time, and the routes with the lowest NO2, PM10 and PM2.5 exposure. With this set of 5 routes, the first 2 are taken into account to quantify exposure, and the least exposed routes are used as a point of comparison to evaluate a possible potential of reduction. Once the concentrations have been obtained on different routes, it's possible to estimate the exposure, which varies according to the specific microenvironment of each mode of transport. Individuals are not in contact with the same concentrations depending on the mode they use. And for example, car drivers are exposed to the concentration inside the vehicle and are consequently not in direct contact with the outside air, unlike cyclists and pedestrians. Therefore, in order to quantify the variations between the microenvironment, a literature review is carried out in the framework of my thesis. So concentrations measured with microsensor were taken from about 40 articles in order to calculate an average exposure ratio between travel modes. So it should be noted that this work is still under development through a collaboration with the Imperial College. So the ratio that you can see in the table there are temporary. Finally, the last level of exposure to be calculated is the dose of pollutant inhaled by individuals. So to do this, it is necessary to estimate the physical activity induced by the modes of transport, and in particular by cycling and walking, in order to reduce the respiratory volume. So the minor ventilation constant, so defined in Zobier work, make it possible to take into account the variation in respiratory volume between cyclists, pedestrians, and car drivers. And for example, in this table, we can observe that the respiratory volume when cycling here is twice greater than when driving. So once all of these parameters have been calculated, it's possible to test the variation of exposure according to mobility characteristics such as the route or the choice of mode. So the influence of the route is assessed by comparing the shortest routes with the least exposed ones. So we calculate the rate of change between the exposure of the shortest routes and the minimum exposure of the least exposed routes for each pollutant. So then the influence of the travel mode is estimated according to the results for the indicators of concentration, exposure for each microenvironment, and the inhaled dose. So finally, the aim of this work is to quantify the total daily exposure by integrating the dose inhaled during commuting, as well as at home and at work. So the doses at home and at work are estimated by taking into account the concentration present at these places, the time spent by the subject in these places, which is about for the work. So for example, at about 8 hours, according to a French national survey, and we take the respiratory volume of an individual at rest, since we do not have precise data on the activities that women carrying out during the day. So we will therefore obtain the total daily dose by adding up residential, occupational, and commuting exposure. And from this information, we will be able to evaluate the weight of each of the specific exposures in the total dose inhaled during the day. So the first application of the method has been done in metropolitan area of Lyon, located in the region of Auvergne-Rhône-Alpes here. In terms of results, some of the data is still being finalized. So this is preliminary results. So we have extracted the data from subjects living and working in the Lyon metropolitan area in 2010, and the routes and associated exposures have been calculated for the same individual by car, by bicycle, and on foot. So this approach is explained by the fact that we do not have yet data on the precise mode used by the individual. So these results are not definitive, but they allow us to observe trends in the exposure of subjects. So the calculated exposure shows that commuting, represented by light green in the 3-circle graph representing each mode, can contribute so up to 18% of the total inhaled dose during the day, of which 2 to 18% of NO2 dose, so represented by the external circle of each graph, and 1 to 16% of the dose of fine particles, so for the middle circle and the internal one. Then the inhaled dose at work, so in the blue part of the charts, represents 1/3 of the total dose, so about 30%. And exposure at home contributes to just over a half, so between 50 and 60% of the inhaled dose over a day. Although the proportion of exposure attributable to travel appears to be quite low compared to residential and occupational exposure, it should be noted that the proportion of time spent traveling to and from work, which represents about 1% for cars, 3% for bicycle, and 9% for pedestrian, is relatively low compared to the time spent at home, so here, and at work. So exposure during travel, therefore, does not appear to be negligible and may vary according to the mode of travel which is used. It can be observed that walking is the most that contributes most to increasing the dose inhaled during the day, followed by cycling and then by car. So this hierarchy of modes can be explained by the fact that active modes induce a higher physical activity, which increases the respiratory volume. But also the duration of journey, which depends on the speed of the mode, implies longer journey times for active modes than for cars for the same distance traveled. In terms of differences between routes for the same mode of travel, It can be observed, for example, for the car, that the fastest and the shortest routes expose on average more than 30% of NO2 and fine particles compared to the least exposed routes. So moreover, the least exposed routes for one pollutant, so for example, the NO2, only slightly increases the exposure to other pollutants. So further analysis is therefore needed to assess the geographical characteristic of the least exposed routes and to also understand to what extent exposure can be reduced during daily mobility. So the choice of mode can influence exposure. It has been observed that the car is the mode that exposes the individual the least, due to lower concentration than for the other modes, and also because of a lower respiratory volume due to reduced physical activity. However, these results should be discussed because it doesn't mean that it's better to use the car rather than an active mode for traveling. And firstly, the method for estimating exposure by car needs to be developed further in the literature review by identifying more specifically how the measurements were made. Indeed, studies have shown that the fact of having the windows open or closed, as well as the air recycling mode on or off, can influence the measure obtained. So in the rest of the literature review, the ventilation parameters of the vehicle will be integrated, and the ratio that you can see here will change. In addition, the question of the benefits of physical activity induced by active modes is also a factor to be integrated for the following work. Studies have shown that cyclists gain an average of 1 year of life expectancy compared to car drivers, but also that the practice of physical activity, including in a polluted environment, would reduce the risk of mortality by 25%. So taking into account daily mobility in long-term epidemiological studies constitute a contribution by studying both the negative impacts of pollution, but also the benefits of physical activity induced by the use of active modes. And this would therefore offer the possibility of conducting studies integrating two environmental factors of cancer, so the pollution and sedentary lifestyle. The next step of my thesis will be to extend the calculation method to the whole of France and for the entire study period. And integrating public transport will also be one of the objectives for further work. Until now, they were not included because the available data do not allow to know if individuals use the bus or the tramway or the subway. So a specific method will therefore be developed. And finally, we are going to start a campaign of measurements by microsensor in the Lyon metropolis from next week. And groups of 4 volunteers will travel at the same time and on the same route in order to measure the differences between mode of travel. And this campaign will make possible to acquire field data, and it will be useful for adjusting the exposure calculation model. So thank you very much for your attention, and I will be happy to answer to your questions later. Thank you.
Thanks, Mary. That was really interesting. The discussion will be at 1 if anyone has any questions. I'm sure there's plenty. Our next presentation is from Madeleine Gyot, Ingrid Pilgrims, Raf Ayert, Eva M. de Klerk. Oh God, I'm so sorry about pronouncing your names this way. Isabel Thomas, I can do that one, and Sophie O. van Beck. So,
yeah.
When you're ready, please take it away.
Yeah, thank you. I will share my screen. Okay, you see my screen well?
No, not yet.
No, okay, it's weird. Ah, yeah, no, I do. Okay, now it will work, I think.
There we go. Perfect.
Okay, thank you. Thank you very much, and thank you to be there today. So I will present you today this paper entitled Non-Response Bias in the Analysis of Association between Mental Health and Urban Environment, and it's a cross-sectional study in Brussels, Belgium. So this paper is based on a project called NAME project that want to study the association between mental health and urban environments. And the study area is so Brussels in Belgium, and it's an interdisciplinary project that bring together epidemiologists, geographer, and medical doctor. One of the challenge in this project was to manage the issue of privacy. Indeed, we had access to health survey and the address of the participants who took part in this survey, but we were not allowed to map health-related indicators. So as a geographer, we receive the XY point and compute different urban environment indicators. And it was only these indicators that could, after that, be linked to health survey and not the address itself. So we compute several urban environment indicators like air pollution and noise. We compute also several indicators of green at different levels. At the house level, we use the view of green indicators. At the street level, we use the vegetation visible from the street, and also we compute linear urban tree density. So we use point data, so the tree that exists in Brussels has a basic unit for that indicators. And at the district level, we use the green coverage within 1 kilometer buffer. In the health survey, we had access to several mental health indicators. There are some that indicate a positive mental health, also general well-being, and other related to mental disorder. And all of these indicators are robust and recognized by the scientific community and are computed from several questions. And we also use social and economic variables present in the health survey. But in this project, we did not find any significant results for the association between green space specifically and mental health. And however, if we refer to the existing literature, there are several international studies that have shown the beneficial effect of having access to green space or just some view to the green, the beneficial impact on the stress and the depression and others. We therefore wonder why such a result. Is there just no association between green and mental health in Brussels? Is it related to the choice of green space indicators? Or maybe is it because Brussels is a city with a lot of social spatial inequality? Indeed, you can see on this map that poor people here have really low green space access. There is also a last possibility, or we see that last possibility, that it's because of the non-response. And on this paper, I will go deeper in that possibility. So we use the data from the Belgian Health Interview Survey. It's made by Cienzano, who is the Scientific Institute of Public Health in Belgium. And we used to survey the 2008 and 2013, and it's based on two parts. There is one face-to-face interview, and then the interviewee have to fill self-administered questionnaires. And the survey is normally answered by the person concerned, but it's also possible that it's done by a proxy, like a parent, a partner, or others, if the people is not available. So taking the 2008 and 2013 health survey in Brussels and only participants over 15 years old living for at least 1 year, we start with a sample of 4,355 participants. And the sampling method used and the weight assigned to each participant make this sample very robust and representative of the Brussels population. But at several points in the survey, participants partially respond to the items that are essential to the continuation of the study. Firstly, some did not complete the self-administered questionnaires. There are two possible reasons for this. Either they were supposed to fill in the SAQ but did not do so, or they were supposed to fill the SAQ, but if a process, so the second possibility is that we're not supposed to fill the SAQ. It's the case that it's a proxy who responds to the survey. And so for the both, it's near 20% of the people. Secondly, at several points during the survey, some did not answer to some item. For a mental health item, this range for 1% to 7% of the participants. And so we finish, so we have the sample of 2,285 participants with all the questions related to mental health answered. And so it's more or less the half of the initial sample. And when we see that, we say, okay, but who are the people? And it's the question what we ask here, who are there and where they live. So what is the socioeconomic and environmental determinant of the partial non-response? And also what is the impact on the analysis of the association between urban environment and mental health. So in order to understand who is not responding and where this non-response is located, we use logistic regression with non-response as dependent variable. And we compare no missing data, so it's the 0, against at least one non-response among the 6 mental health indicators, so it's the 1. For those who don't know this graph, it's called forest plot, and they are allowed to they allow the visualization of the result of logistic regression. So here you see each mustache represents an odd ratio. An odd ratio significantly greater than 1. So in that part of the graph means that the explanatory variable increase the probability of non-responding. So it's a risk factor. And if the odd ratio is lesser than 1 in that part of the graph, it means that the explanatory variable decrease the probability. So it's a protective factor. And we saw that the partial non-response was higher among lower income here, older people here, and they are also higher among the couple with child, also one parent with child compared to a single people. We saw also that less educated people have this risk factor to not respond. And we use the year of the is as a confounder, and it's also significant. Now for the urban environment, so we compute 2 models. The first, it's a single exposure model, and in the second, it's the same, but we adjust for the sex, the age, and the income. And we see that partial non-response was higher in low vegetation cover, more polluted and more urbanized area. And it's even significant when we adjust for sex, age, and income. So it was the first part of the study, and then we say, okay, so we see here that it's maybe a risk profile also, not just to non-response, but it's also quite the same profile that people who have mental disorder. And so we want to explore a little bit more to see if it's really related to be to have more risk to non-response and to have more risk to have a mental disorder. So we compare, we do quite the same analysis, but just with the non-response to depression as dependent variable, and we compare that to the fact to be depressive or not. So it's not the same population, because here it's all the respondent to the study, and here it's just the people who answer to the question. Otherwise, we do not have the data. So here it's both model, in red the probability to not respond, and in blue to be in bad mental health. And we see that there is some resemblance and some difference. So we saw that poor people are both a risk factor to not respond and to be in bad mental health. We saw also that just for the very young people who are more likely to respond and more likely to be in good good health, good mental health. And also we saw very the same results for the people with low educated that are more risky to not respond and to have a mental health problem. In red, we see the very different thing we found. So the gender, it was not significant for the fact to not respond, and to be a woman is a risk factor to have mental health problem. We saw also very different results with the family composition. We see that people with children are more risky to not respond, but are more, it's a protective effect for the mental health. And there are some results here in yellow that we cannot really say if it's in what sense we can analyze it. So the results show that the risk profile for mental health have some similarity with the risk profile for non-response, and it's there is significantly more non-response in place with low vegetation coverage. So we can assume that we would be proportionally have a bigger pool of respondents here than the pool that we the pool that we actually observe due to non-response. So the real C is bigger than the C we observed in the complete sample. And considering the equation of an odd ratio, we may conclude that the odd ratio, the true odd ratio will be less than the, will be smaller than the odd ratio that we observed. And based on the existing literature, we would have expected to observe an odd ratio smaller than 1, thus a protective effect of the vegetation. And therefore, the protective effect of green space on mental disorder would be maybe underestimated because of the non-response. It's just a possibility because we do not have the data, because there is not the response, so we don't know, but we think that it could be really a big effect. And the key message of that paper is first that the non-response, it's a large percentage. Also that the non-response, it's not random, and it's made that the relation between urban and mental health, it's more difficult to analyze. And urban health is complex, and with the non-response, it's even more. So thank you for your attention. And I'm finishing now. I know that it's less time that I have, but I think it was enough to explain my paper. So thanks.
Fantastic. Thank you, Madeleine. We are okay to finish early once in a while. No need to worry. Our next presentation is from Stefania Bertazon, Caitlin Calder-Bellamy, Rizwan Shahid, Isabel Kuoloigner, and Yui Tanagi. Again, I'm going to apologize every time I say people's names, just as a blanket statement. Are you guys ready?
Yes, I am good to go. I'm just going to share my screen quickly here. Okay, perfect. Oh. Okay, can everyone see?
Fantastic, thank you.
Okay, perfect. So hi everyone, my name is Caitlin Calder-Bellamy. I am in my 4th year of a undergraduate degree looking at biomedical sciences and geography. I'm super excited to be here today. I wish I could be there in person. Nevertheless, super excited. And over the past summer, my colleagues and I have decided to look at the associations between childhood asthma, air pollution, and socioeconomic status in Calgary, Canada. So let's get started. Oh, goodness. Okay, perfect. So before we get too into the nitty gritty, I want to bring us through a brief sort of outline of what we'll be talking about today. So to start, we'll dive into some background information. So what is asthma? How does air pollution affect asthma? Secondly, we will be looking at the current state of knowledge. So what do we know currently about these relationships between asthma in children, as well as air pollution and socioeconomic status, specifically in Calgary. Then look into some methods and data collection, followed by the fun stuff, the results, and then at the end get into some sort of conclusion and future directions. Perfect. So what is asthma? So asthma is the most common chronic lung disease in Canadian children, with approximately 850,000 asthmatics who are 14 years and younger, which is a pretty hefty, substantial portion of the population of Canada. Asthma is characterized by inflammation of the airways, so difficulty breathing, cough, wheeze, so on and so forth. And asthma is actually one of the primary causes of respiratory hospitalization among Canadian children. So definitely an issue we want to be looking at here. Asthma prevalence has actually increased in Albertan children under 14 years in the recent years. So again, sort of cause for more investigation. And actually both traffic related and environmentally related air pollutants are common causes of asthma exacerbation, which is an acute worsening of symptoms. Children might be especially susceptible to this exacerbation because of their underdeveloped lungs. Compared to adults, they also breathe in more polluted air per body weight compared to adults. So something to look at for sure. So what do we currently know about these relationships? Well, my group, Dr. Stefania Bordazone and I have looked at a sort of a similar project in the past years, looking at the relationships between asthma of all ages though, and air pollution in Calgary. We found that spatial autocorrelation of asthma emergency visits is actually increasing over time, which indicates that these asthma exacerbations, these visits might be more localized and segregated to different LGAs. You can kind of see these LGAs here in the graph on the right, 16 in the city. We also found that areas with higher asthma emergency visit rates are congruent to areas of higher industrialization. As you can see over here in the east of the city, there are increased sort of visit rates as opposed to over here in the west area of the city. When looking at pollutants, we found that asthma exacerbation, or as these emergency visit rates, were consistently correlated to 3 of the 5 pollutants monitored, including BTEX, which is a combination of 4 different volatile organic compounds, as well as PM2.5, which is short for particulate matter with a diameter of 2.5 microns or less, as well as PM10, which is a particulate matter with a diameter of 10 microns or less. We also looked a little bit at the low income status here, and we found some strong correlations between asthma emergency visit rates and these the low income status. So with this information, we found this to be quite notable, as well as the increasing prevalence of asthma in children. So we decided to therefore look at the relationships between childhood asthma exacerbations, air pollution, and socioeconomic status in Calgary, Canada. We use asthma emergency visits as proxy data for asthma exacerbations, again, that acute worsening of symptoms so much that you need to go to the hospital room for assistance. We also found seasonal differences, monitoring both summer and winter months, so getting a look at how the different seasons affects these relationships. And we did this over 5 years, so a study period between 2014 to 2018. So let's get into some methods here. So we first looked at some descriptive statistics, looking at three main variables, including asthma ratios, air pollution, and the material deprivation index, or MDI for short. Then we ran some Spearman correlations at the city level, the quadrant level, and the LGA level, where each data point was represented by a sublocal geographic area, or SLGA. And these SLGAs, there are about 200 in the city and about approximately 1,000 people minimum as a population. So we get a pretty decent idea of how people are distributed throughout the city. Anyway, so looking at the city level, we incorporated the full scope of Calgary. At the quadrant level, we split the city into four. So the northwest, the northeast, the southeast, and the southwest correspondingly, and also the LGA level. And this graph on the right here shows you nicely all these 16 LGAs within the city. We ran these correlations between all three of our main variables, including asthma ratios, air pollution, again, and the material deprivation index, just to get a decent idea of how these variables are applied together, how the relationships intersect. We finally had some time to look at some spatial statistics, so Moran's I and Gaddis G, looking at the spatial autocorrelation and clustering of said variables throughout the city. So let's look at some data collection here. So to monitor these asthma emergency visits, again, as asthma exacerbations proxy data, we looked at these visits for children 14 years and under at the sublocal geographic area. And this data was acquired from the Alberta Health Services after ethics approval from the University of Calgary. And to kind of normalize for the amount of children at each SLGA, we looked at the number of visits per SLGA and then also the number of children 14 years and under SLGA. And this data was acquired by the 2016 Canadian Census. So when we're looking at asthma ratios overall, we looked at the number of children who had an asthma exacerbation, so went into the emergency room, and then divided that by the total number of children within this SLGA. Get a better idea of how many children per SLGA are affected by this. Then we looked at air pollution data, and this air pollution data was acquired by a campaign acquired by the Canadian Health. And this was done by my supervisor, Dr. Delphine Praud, and her group. And then looking at the socioeconomic status, we used the material deprivation index, which is a part of the Pampelon index. The Pampelon index is used to monitor socioeconomic inequalities within Canada. It's composed of both a social deprivation index and a material deprivation index. Interestingly, the material deprivation index is the most relevant to the Alberta context, so we use this. And it is combined of three different variables. So education, employment, and income. These three variables are combined to create that MDI, which is then split into quintiles. And using these quintiles at the SLGA level, and the sub-LGA level, we use this as an indicator of socioeconomic status in Calgary for the project. And here we kind of get a visual of what the air pollution estimates are looking like. Again, this was done by Dr. Delphine Praud and her group. And these campaigns were actually done in both 2010 to 2011, and then again in 2015 to 2016. And we found that the air pollution over the years has remained quite consistent, which allowed us to use the 2015-2016 models for our research. So we looked at 5 different pollutants, including nitrogen dioxide, which is NO2, again, PM2.5, which is particulate matter with a diameter of 2.5 microns or less, particulate matter 10, again, particulate matter with a diameter of 10 microns or less, black carbon, which is actually a subset of PM2.5, but mainly a result of biomass combustion and fossil fuel combustion, as well as BTAX, which is, again, a mixture of 4 volatile organic compounds, including benzene, toluene, ethylbenzene, and xylene. So NO2 and PM2.5 are common traffic-related air pollutants, whereas PM10 is more of an environmental air pollutant factor, kind of monitoring dust, pollen, so on and so forth. Again, black carbon is a result of fossil fuel and biomass combustion, and BTEX can be a result of vehicle exhaust. You can even be exposed to this at the gas pump, as well due to combustion even of airplane fuel, for example. Awesome. So to get started, we kind of wanted to look at the distribution of children as well as the distribution of the material deprivation index to get a decent idea of how things are spaced throughout the city. So at the distribution level here, we see the percentage of children within the area, where the lighter color represents a smaller percentage of children and the darker color represents a higher percentage of children. And with this, we found these quite as to be expected, as the darker color here kind of seems to act as a perimeter almost around the city, really reinforcing the idea that children do live in the suburbs and less so in the city center. When looking at the material deprivation index here, we see that there is kind of a spatial almost gradient-like increase towards the northeast quadrant of the city, where the northeast here shows a higher deprivation index, again, where 1 equals the least deprived and 5 is the most deprived. Again, the lighter color is least deprived and the darker color is most deprived. So again, it's sort of gradient-like increase here. Awesome, so here's the fun stuff. So we're looking at the results. And first we looked at the correlations between asthma ratios and air pollution in the city. This was done at the city level. And you can see quite minimal, but some significant correlations in the summer and winter months of 2015. There's not much here, so we kind of dive deeper into the quadrant level, and our most notable results were at the southwest quadrant level. And we found quite significant correlations between particularly PM 2.5, again, that traffic-related air pollution, and asthma ratios. And again, these are negatively significant correlations, which we found to be quite interesting, since it is a common traffic-related air pollutant and which is commonly associated with asthma exacerbation, even in children. And so we found that these data suggest that air pollution or outdoor air pollution might not be the primary cause of asthma exacerbation in children, but instead other factors, potentially even indoor air pollution. So then we looked at the correlations between asthma ratios and the material deprivation index, first off at the city level. And we found that we had some weak but significant correlations earlier on, so within 2014 up to 2016. And these are primarily in the summer months as well, as opposed to the winter months. So we see that there might have been some sort of spatial segregation between asthma ratios between 2014 and 2016, but in recent years, we see that correlation really come down to suggest that there might be decreasing health inequity in the city of Calgary, which would be quite a positive thing overall. So we dove again a bit deeper and looked at the quadrant level, and our most notable results were the southwest quadrant, which is quite interesting. We see a decrease in correlations overall, where our most significant correlations, again, earlier on 2014 up until even 2016. And these stronger correlations here suggest, again, that indoor air pollution might be more of a cause of asthma exacerbation in children as opposed to outdoor air pollution. This might be due because indoor air pollution has been consistently correlated to lower socioeconomic status as a result of poor ventilation, dust, and mold in these homes. Again, you see over time that sort of decreased health inequity, again, a very positive thing we want to see in the city. And we found these results to be quite notable, as both the northeast and the southeast quadrants, as we've seen, have an increased material deprivation index. So we kind of expected to see more correlations there, but there weren't too many significant values, which might be a result of sort of a consistent material deprivation index over space and time. Awesome, so then we took a look at the air pollution and material deprivation index. And our most notable findings were at the quadrant level. So we see at the northeast quadrant, quite a semi-industrialized area. We see a negative significant correlations in both summer and winter months between pollutants, which was quite interesting. And this might be due to sort of similar air pollution spatial temporal results, as well as similar MDI results over space. Not too much variation there, so it might be due to that. Whereas interestingly, in the southeast quadrant, again, another sort of semi-industrial area, we see positive correlations between air pollution and the material deprivation index. This might be, again, due to more variation between both variables, but definitely something interesting and quite notable. Awesome. So now we're getting into the spatial statistics, looking at asthma ratios. We didn't find anything significant here, but as we can tell by the mapping, we see almost a sort of spatial increase in the summer months towards the northeast quadrant, almost in a gradient-like motion again. So you can see in 2014, the northeast quadrant here, there's some pale color. And as you kind of get over into 2017, 2018, you see this darker color indicating increased asthma ratios. Then we looked at air pollution, and again, you see this gradient-like increase towards the northeast, where especially in the winter months. So we found strong and significant spatial statistics looking at Moran's I and Geddes G for all pollutants in the winter months at the SLGA level, and most were significant in the summer months, as well. So then we took a look at material deprivation index, and again, similarly, you see that increase, gradient-like increase towards the northeast. And here we found both strong and significant spatial statistics as well. So we're really starting to see that relationship in the gradient-like increase in some asthma ratios, as well as air pollution and material deprivation index. Awesome. So just to get into a few kind of take-home messages. So our correlation suggests that there might have been some health inequity within the city, especially among children, but this seems to be decreasing over time, which is quite a good thing to see overall. However, this mapping that we've done looking at asthma ratios has suggested that asthma exacerbation is becoming more prominent in areas of lower socioeconomic status, particularly during the summer months. We also found that spatial statistics indicate a clustering of outdoor air pollution and a material deprivation index in Calgary. But with this said, we found that the primary cause of asthma exacerbation in children might not be outdoor air pollution at all. It might be a result of indoor air pollution. It could also be due to allergies or even cold temperatures, since Calgary can get quite cold in the winter times. And with this said, we think that we should take this study a little bit further and look at areas where children frequent the most, and looking at how both the spatial temporal mapping of air pollution in those areas, including parks, schools, and areas of active transport. Awesome, so just some references. And before I go, I just really wanted to quickly acknowledge some people. So firstly, Dr. Stefania Bortizone, which was my supervisor. Secondly, I wanted to acknowledge Alberta Innovates for the support in this research, as well as the CIHR Institute for Population and Public Health, as well as the O'Brien Institute for Public Health. Thank you so much. I've really enjoyed sharing my research with you.
Thank you very much. That was fantastic. I just have to reset. There we go. Our next speaker is not Lény Grassot. It is Delphine Praud. Are you there, Delphine? I think you're muted. I can't hear you.
Sorry. Thank you. Yes. Okay. Can you see my presentation?
Yeah, looks good.
Thank you. So good afternoon, everybody. Thank you for the opportunity to present our project. So I'm Delphine Praud, and I will present the work of Lény Grassot, who apologizes for his absence today. So today I will presenting a research on how local historical information can be a proxy for environmental exposure to air pollution in the French context during the 20th century. This work takes part of an epidemiological project on breast cancer. Breast cancer is the first cancer in women in terms of patients number and in terms of death number. Among breast cancer risk factors, exposure to air pollution is suspected, particularly chronic exposure or specific exposure during critical sensitivity periods. And thus, epidemiological studies on cancer need historical data because of the known latency between exposure and incidence. However, regarding air pollution data, there is a lack of information before the year 2000. To work on this limitation, we developed the RHQ project for a residential history questionnaire. We are working on data of a French cohort of women named E3N cohort, initiated in 1990, recruiting women aged between 40 and 65 years old. And based on this cohort, we developed the RHQ project, a case control study nested in the E3N cohort, including 2,876 breast cancer cases and 3,616 controls, so subject cancer-free. And we collected all postal addresses of the included women from their birth in order to consider the lifelong exposure to air pollution. So for this, we aim to explore a pollution surrogate from available historical data since 1920, so with specialized data. In order to reconstruct adequate historical data, it is necessary to take into account a few constraints. So for all data, we need to have national spatial coverage and sufficient temporal coverage, that the information covers the entire mainland France, and also that it need to covers at least 100 years, at least since 1920. And for pollution data, we need to have the recent data that cover a sufficient time period to approach a robust extrapolation into the past. And for historical data, we need regular enough data that they offer precise enough spatial granularity, or lastly, they do not evolve over time. The data currently used are historical data. So we used the data from the regular communal censuses since the end of the 19th century for the French National Institute of Statistics and Economic Studies, the INSEE, and invariant geographical data collected from the French National Institute of Geographic and Forest Information. And for pollution data, we used a multi-scale chemistry transport model provided by INERIS on the whole European continent. And in this exercise, this pollution data covered the whole French territory since 1990. And we average annually to the territory of each municipality. Oh, sorry. Sorry, okay. So in detail, the demographic data are the municipal population, also the so-called local population indicator, when we take into account the surrounding municipalities modulated by the distance squared, as well as the density, the rank, but also the evolution over 10 or 20 years. The spatial data are on the one end the ones we call invariants, such as latitude, elevations, distances to neighboring countries, and also distances to the oceans and seas. And we also used the land cover from the Dutch research project HILDA, which proposes a European coverage over 100 years on a kilometer resolution for 6 classes, including the settlements. Finally, for the pollution data, they are derived from various available models, and we consider different resolution data. a resolution of 8 per 8 kilometers from 1990 to 2010, a resolution of 4 per 4 kilometers from 2000 to today, and a resolution of 1 per 1 kilometer from 2009 to 2013. So we use two complementary approaches. First, the univariate approach will look at the correlations between the historical and also spatial variables and the pollution data. So we looked at the disparities between the different pollutants and resolutions, as well as the synthesis for each variable's relationships with the pollution dataset, but also studying the historical trends. And the second approach will jointly exploit several variables to find one or more models to estimate the exposure in order to select the best one. So first, for the univariate models. So the explorations of the models begins with a pairwise analysis of the set of variables. By taking into account the proximity and distance between the variables and the groups, we initiated first sorts. So for example, we can see here that there is a strong lack of correlation between the raw demographic data, so the first 10 lines, and the evolution data of this same demographic data. So here the correlation is very low. And there is no columns that stand out in either red or blue. We can also see that no single data item seems to be strongly linked to the pollution dataset, as we can see here. And focusing on correlation between pollutants, we found strong relationships between NO2 and particulate matters. And conversely, an opposition of ozone to the three others pollutants. And also spatial scales do not appear to alter these relationships. To validate the exploration of the variables during time, we verified if the relationships remain constant over time. So here we can see a selection of the most used variables to illustrate the correlation stability despite time, and this over nearly 30 years. And we can see that the relationships remain stable over time. So this result is very important to argument in order to extrapolate in the past. And this conclusion is also true for the whole historical dataset. After that, in order to select the most relevant variables which represent well the different pollutants, we attempt a summary of correlation. So here we computed the average of the adjusted R squared of the 12 pollutants. And here we can see that the latitude appears to be the most related to pollutants concentration. And using communal density as a reference, we can see that several variables appear to better capture the different pollutants exposure and resolution. First, we can notice here, framed in yellow, that invariant standouts such as elevation and also distances to sea or oceans. And framed in green here, we can see that the ranks show a strong potential compared to the corresponding continuous data. So here we can see the communal density rank, and which is more correlated than the communal density considered in continuous. Finally, here we represented especially the difference between the raw pollution, so the pollution estimated with Chimère, and the data estimated with the models. Here we took as example the difference with the model using local density rank in 2010. And we can see here that strong spatial heterogeneities with extremes over or under exposing area of the territory. We therefore sought to explore the multivariate models. So here we illustrate the approach with NO2 with a resolution of 8 × 8 kilometers for the period 1990 and 2000 until 2010, for which data on NO2 were available. And by systematically exploring multivariable models up to 7 variables to limit complexity, we compare the results of all models using the adjusted R² and also the Akaike criterion. And here a model with only 3 variables achieved R² of 0.7, which includes latitude, communal density, and also the population, the rank of the commune in terms of local population when we take into account the surrounding municipalities. And while including 7 variables allows to increase the R² to 0.8. It is therefore possible to visualize the distributions of communal exposure estimated by each selected models. Here we can compare the exposure of the data provided by the Chimère model, so the raw data in pink, to the model estimated with the communal density in red, the latitude in yellow, the 3 variables model in green, and finally in blue, the 7 variable model. And we can see that the more the model is refined, the more the distribution is close to the raw data. Here we represented differences between the model and the initial data with the same 4 models seen in the previous slide. And the multivariate models, so the 2 top ones, show much smaller deviations than the model with the latitude and the density. And here we compared the spatial impact of the model by taking the initial data, so the data exposure estimated with Chimère as reference. We can visually compare to the 4 other models and also compare the respective differences. So here in the second line, and this map illustrates the refinement of the results with the complexity of the model, but also the differences that remain. For example, here in blue, we can see that high altitude are underestimated, and the land's coastline in the west is overestimated. So in conclusion, we can say that it seems relevant to explore this data to assess historical environmental exposure. Our development of a methodology to evaluate past exposure with different types of variables and modality leads to some interesting theoretical and methodological results. In the demographic analyzed variables, ranks reflect potentially greater interest than continuous variables. And then for the models, nevertheless, our investigations are not finished, and we seek to continue exploring the compared models with more refined methodology, integrating new data and trying to provide a single model for all airborne pollutants. And finally, concerning the HRQ project, the epidemiological analysis of the associations between the estimation of these models with breast cancer risk are in progress. So thank you for your attention, and do not hesitate to contact us if you have any questions.
Thank you very much for that. That was fantastic. We are coming up to the end of our presentations. Our final show is from Guoqiang Wu, Alison Heppenstall, and Nick Lomax. Are you guys here?
Yeah, hello everyone. I'm
Hi.
Guoqiang Wu. Can you call me Chris? Yeah. So I'm going to sharing my. Okay, just give me a second. So can everybody see my screen now?
It looks great.
Okay, great. Okay, hello everyone. My name is Guoqiang Wu, and I'm going to present our paper, which is titled as Estimating Health and Social Outcomes as Small Areas in Great Britain by Generating and Utilizing Synthetic Population Data, and based on project CYPER. So firstly, I would like to have a brief introduction about the CYPER project. So basically, CYPER is short for Synthesizing Public Health and Health Economics Research, which is funded by the UK Prevention Research Partnership. As you can see, the overarching of CYPER project is to co-develop with policy partners and new synthesized economic evaluation methods that used to be informed design, implementation, and interactive intelligence-led refinement of lung health sector policies that prevent lung communicable diseases and health inequities. There are 4 policy areas we are particularly examining, including the inclusive economic growth, the housing, public mental health, and advanced childhood experience. So the collaborations has been made between 7 universities in UK and 3 policy partners from the Sheffield City Council, the Greater Manchester Combined Authority, and the Scottish Government. So here I'm just showing all the partners leading to the huge CYPER consulting. There are 80 integrated work strands in CYPER, and the objectives of 8 work strands form the wheel of CYPER. So in University of Leeds, we are responsible for 2 work strands of data and system monitoring and policy microsimulation. So in this stage, we are currently focusing on the workstream 3, which includes identifying relevant data and negotiating access to data for use by the CYPER, and also looking after the data, ensure it is stored securely and that is of good quality, and linking to other data where appropriate. And also more importantly, in the creation of a synthetic data set for Sheffield, Greater Manchester, and Scotland using spatial microsimulation. Firstly, I would like to address some terminology issues. So what are the spatial microsimulation and the population synthesis? So according to the Lovelace and Dumont, the spatial microsimulation is a creation, analysis, and modeling of individual level data allocated to geographical zones. So this concept can be further explained by the 3 elements, spatial, macro, and simulation. So firstly, spatial maximization is concerned with how things vary over space, not just between individual groups or period of time. So this is the spatial dimension. And secondly, spatial maximization explore issues at individual level, as implied by the word macro. And thirdly, the spatial maximization involves the creation of fictitious data for multiple purposes captured by word simulation. And on the other hand, the population synthesis is a set of the techniques of generating individual level data allocated to geographical zones. So, and it is an important component of spatial microsimulation approach, and it aims to generate a realistic sample for each area that is as similar as possible to aggregated level constrained data. So to illustrate the process of spatial microsimulation and more vividly, I'm showing this picture. So you can see that the general survey data constraint contains rich attributes of individuals such as age, behavior, or habit, disabilities, and wearing. However, they don't provide the specific geographical information for each individual. So by contrast, the constraining data are geographically aggregated, but they don't provide many individual attributes. So after spatial maximization, individuals with rich attributes in the survey data are duplicated and allocated to different geographical areas specified in the constraining data, so that we can know individuals' both attributes and the geographical information. The population synthesis using spatial maximization involves the allocation of individuals from a survey dataset to administrative zones based on shared variables between the area and individual level data. So in our case, we used the 2011 census data and the ONS and NRS, which is National Record of Scotland, media 2018 published estimate as the geographically aggregated data, and using the Anderson Society survey with 9 data as individual level data. So as for the method of modeling, we use the statistical combinatorial optimization approach, which is called simulated annealing. For the input data, the geographically aggregated data are called the constraint, and the individual level survey data are called the micro data. So the constraints have zone ID indicating each geographical area, whereas the micro data contains each person ID indicating each individual. After allocating each individual to different geographical zones according to the attributes variables by using the parallel optimization, a spatial microdata containing both zone and person IDs will be generated, and that is the output of synthetic population. At last, the validations will be made for the population data in comparison with original input data. This is general process of the population synthesis using spatial maximization. So as I said, we use Anderson Society survey data as the individual level input data. For the adult sample, we select out and recode the 7 linking variables, which are shared between the individual and the aggregated level data set. So this table shows the format and structure of the individual level data containing the person identifier and the 7 linking variables. So this table is just an extract example showing what the categories looks like for each linking variable. We used with 9 of Anderson Society survey data to create our individual level data set with cases interviewed in the year of 2018. So the total valid sample size is over 13,000. So corresponding to the 7 linking variables, 7 constraint tables are created by using the 2011 UK census data and the mid-2018 published estimate at the LSOA, which is lower layer superoutput area, geographical area level, which is a UK census small geographical area. In our model, we are focusing on the 4 city regions of Manchester, Sheffield, Glasgow, and Cardiff. So the example table of the 6 by age just give you an overall look of the constraint variables we used in microsimulation model. So the 6 by age constraint is derived from the ONS and the NRS and mid-2018 published estimate data, and sets the baseline population of our model in 2018. So this is a summary of the constraint variables used our microsimulation model and the source data set from the 2011 UK constraint tables or mid-year published estimates. This diagram shows the overall methodological framework of spatial microsimulation and population synthesis. I know it's hard to say clearly, but basically the 2 microsimulation submodels are created and run separately for adults and children. So the individual level dataset inputs of 2 submodels are both from the Anderson Society survey data. For the child microsimulation model, it's quite simple with only constraint of 6 by age. For the adult model, the 6 by age tables from the mid-2018 population estimate will persist into the 6 by age constraint and set a baseline population for our microsimulation, because it provides the most adequate and reliable population count in the year of 2018. Other 6 census tables were scaled to the baseline population before they led to the other 6 constraints for adult microsimulation model, so that we can ensure we synthesize the population at 2018. The method we use to undertake spatial microsimulation is based on the simulated annealing algorithm. So generally, it proceeds by randomly selecting the adults from the microdata and considering them for the attendance to the population of a small area if they improve the good fits of the population to the constraint tables. So the aggregation and fit evaluation is repeated, and the new individuals replaces old ones in small areas if the fit is improved. In terms of the modeling environment, we used a bespoke software framework, which is a flexible modeling framework, the FMF, to undertake the microsimulation process. So the FMF, which is developed by the University of Leeds, incorporates a static spatial microsimulation algorithm based on the simulate annealing. It also has a graphical user interface, which allows the users to select input data files and specify required linkages and options and outputs. In addition, the FMF includes a model evaluation function that enables internal model validation by calculating the various good fit statistics. And the outputs of the microsimulation is a synthetic population table, which only contains 2 columns: the LSOA code, which is the zone ID, and the ID of the persons, which is PIDP, allocated to each LSOA. In our case, we synthesize total adult population of over 61 million in 4 city regions in Great Britain at the year of 2018, across over 5,800 LSOA. So by linking the synthetic population output table with Anderson society survey data through the personal identifiers, we can get the baseline synthetic population microdata with multiple personal and household attributes, including the key variables of interest like income, health, and subject well-being. The baseline synthetic microdata can be then aggregated to do some spatial distribution analysis. These are some examples of aggregation and distribution analysis using the synthetic population output at the LSA level for the 4 city regions regarding the key variable of interest. For example, the subject well-being Likert score for the Manchester city region. Another example, the subject well-being, which is measured as a case score for the Cardiff city region. And this example of people's overall physical health performances measured as SF12 physical component summary score in Sheffield. And the last example, the overall mental health performances measured as SF12 mental component summary score in Glasgow. To validate the synthetic population data internally, we calculated 4 goodness of fit statistics for each constraint variables, including the R-square, the SRMSE, and RE, which is a relative error. So generally, this statistics show that the model fits the original data quite well. And for external validation, we firstly compared our simulation results with index of multiple deprivation data in England, Wales, and Scotland, which indicates IMD rank for each LSOA. A higher IMD rank indicates a higher level of deprivation. We aggregated the health and income variables information at LSA level and joined the IMD rank information from the IMD data through the LSOA code. Then we examined the correlations between the IMD rank and our LSO level estimates regarding health and income. The right table shows that except for subjective well-being, which are reversely scored, all income and health variables are positively and significantly correlated with IMD score, which means that the higher IMD rank suggests the lower income and worse health situations and the more distressed feeling. So this result proves that our synthetic population data are valid. Sorry. We then aggregated our simulation results from LSOA to a higher MSOA level and compared to our MSOA level as simulation result regarding the annual household net income with the 2018 ONS income estimate for small areas, which is IESA in England and Wales. Sorry. The ONS IESA datasets report both the upper and the lower annual household income estimate limits for each MSOA in England and Wales. And from the diagram, you can see that our simulated income estimate at MSOA levels generally fluctuate between the ONS upper and the lower estimate limits. In fact, our microsimulation results fall within the ONS confidence intervals of income estimate for the overwhelming majority of MSOS in the 3 city regions in England and Wales. And more specifically, the simulated income results are generally consistent with ONS income estimate in over 90% of the total MSOS. So again, our synthetic population data are valid. There are different ways to utilize the synthetic population data. For example, we can aggregate the data as small areas for spatial analysis, just like what I showed before. We can also cut the data to target specific population segments, such as a low-income population and the poor health population. Besides, we can calculate some summary metrics based on the synthetic data. For example, we are now calculating the different inclusive economic growth indicators using this synthetic data. We can also attach additional data, such as IMD data, the child poverty data, and the earnings data for further analysis. Additionally, we can do some experimental with policy interventions at the individual level. And last but not least, we can use the synthetic data as an input into other models, such as the dynamic microsimulation model. And that's what I want to share with you. Thanks for listening.
Right, thank you very much. It is now time that we have a bit of a discussion. I'm going to switch this over to grid view so we can see you all in the recording. If anyone has any questions, now is the time. We finished a bit early, so we have quite a bit of time left. It's an open floor, so if you have a question, just unmute yourself, say it out loud, or if you'd rather I read it for you, you can put it in the chat. I can read it out loud, or people can answer it there. The floor is now open. If there's any questions at all, please go ahead. Seeing no questions so far, I suggest we wait a few minutes, and if everyone's extremely bored and nobody wants to ask anything, nobody found anything tonight useful or interesting, I'd be very surprised, but also we can call the meeting a day there. So let's wait a few minutes. If you have any questions, please feel free. Interrupt me if I'm talking when you come up with one. Discussion is an important part of the presentation. In that case, let's take the positive view. Not everyone was bored. Rather, everyone presented so clearly, there's nothing left to be asked. We understand everything perfectly. Health and well-being, very easy to get, we're all there. I'm going to stick around for a few minutes. If you feel that you want to go for lunch, you are welcome to leave early. I'll be here if anyone has any more questions at all. Right, that being the case, thank you everyone for coming to this special session on health and well-being. Don't forget, there is a keynote lecture from Professor Rachel Franklin at 3 o'clock. Make sure you go to that. It's supposed to be fantastic. Thank you so much for coming. I'll hopefully see you all soon.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you.
Bye.